Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at finding the derivative of the inverse tangent function. In the last video we took a look at how we find the derivative of the inverse sine and the inverse cosine function. We're going to do something very similar in this video, except it's going to be the inverse tangent function. And as I mentioned in the last video, this notation is not, don't think of it as an exponent, just think of it as notation to represent inverse tan. Do not treat it like an exponent. In order to differentiate this, we could express this instead of as an inverse tan function, we could rewrite it as a tangent function. So if y equals the inverse tan of u, then tangent of y will equal u. So that's representing the same function. Then what I'm going to do is differentiate implicitly. So the derivative of tangent of a function will be secant squared of that function. We're differentiating with respect to x, where y is a function of x, so the derivative of y with respect to x is dy dx. The derivative of u with respect to x is du dx. We can isolate dy dx by dividing both sides by secant squared y. Just like in the last video, we don't want to express the derivative of our function, inverse tan of u, where u is a function of x. We don't want to express that in terms of y. So again, we're going to use one of our trig identities, one of the Pythagorean identities, that says 1 plus tangent squared theta will equal secant squared theta. So I'm going to replace secant squared y with 1 plus tangent squared y. You'll see why in a minute. So that's going to be 1 plus tangent squared y. And we know that tangent of y is equal to u. Therefore, I can replace tangent squared y with u squared. Now my derivative is in terms of u. So when I've got y as an inverse tan of u, this is the derivative formula that we're going to use. Let's take a look at some examples where we use this formula. Our first example is a fairly straightforward one. You might want to have your inverse tan derivative formula handy so you can refer to it. The derivative of inverse tan of a function, or inverse tan of u, is 1 over 1 plus u squared. So my u is 3x. Then chain rule multiplied by du dx. The derivative of 3x is 3. We'll just write that as 3 over 1 plus 9x squared. That's it. That's the derivative. In our next example, our u is x squared minus 4, but it's an inverse tan function. So when we differentiate, it's going to be 1 over 1 plus the u squared, so x squared minus 4 squared. Then we multiply by the derivative of x squared minus 4, and that would be 2x. Then we just simplify it a little bit. We're going to FOIL this, so that's going to be x to the 4th minus 8x squared plus 16 x to the 4th minus 8x squared plus 17. And we're done. Let's try some more. In our next example, we have a product, 2t times inverse tan of 5t. So I've just made note of the product rule, and I've identified the u, found the derivative. This is the v, and the derivative of that is 1 over 1 plus 5t squared times the derivative of 5t. So I'm just going to plug all of these things into our product rule. So the derivative will be u, which is 2t, times v prime, which will be 5 over 1 plus 25t squared, plus v inverse tan of 5t times du prime, but I'll put the u prime out front. And we can clean it up just a little bit. 10t over 1 plus 25t squared plus 2 times inverse tan of 5t. That's it. Next example involves a quotient. So we have x to the 4th plus 1 in our numerator. That's our u. So the derivative of that will just be 4x cubed. Our denominator will be the v, which is inverse tan of x squared. So when I take the derivative of that, it's inverse tan function, so the derivative is 1 over 1 plus this squared, the x squared squared, and then we multiply by the derivative of x squared, which is 2x. Now I plug all of those values into the quotient rule, so the derivative will equal inverse tan of x squared times u prime, which is 4x cubed, minus u, which is x to the 4th plus 1, times v prime, which when I simplify this will be 2x over 1 plus x to the 4th. All of this is over inverse tan of x squared squared. Remember, this isn't an exponent, so we can't use any of our exponent rules. We're going to leave it in this form. And when I simplify this, my numerator will be 4x cubed times the inverse tan of x squared minus, notice the x to the 4th plus 1 cancels with the 1 plus x to the 4th, and we're just left with 2x. And there's nothing I can do with my denominator. It's this whole thing that's squared, but I can't express it any differently. So that's my answer. Let's take a look at one last example. So with this example, it is an implicit function, which means we need to differentiate every term with respect to x, our independent variable. And whenever you differentiate y with respect to x, you should end up with a dy dx. So we'll start with this term, the inverse tangent. We know the derivative is 1 over 1 plus our u, which is 2xy squared. And then we multiply by the derivative of this. This is a product. We have 2x times y. So we use our product rule, and our derivative will be 2x times the derivative of y, which is dy dx, plus y times the derivative of x, which is just 2. The derivative of 3x squared is 6x, and the derivative of 8y is 8 dy dx, and the derivative of 4 is 0. I'm just going to square each factor there. So that will be 4x squared y squared. I have a fractional equation, and what I usually do when I have a fractional equation is I multiply through by the lowest common denominator, which is this denominator. So I'm going to multiply both sides of my equation by 1 plus 4x squared y squared. And that allows me to eliminate that denominator. So I'm left with 2x dy dx plus 2y equals, I need to FOIL 6x plus 24x cubed y squared minus 8 dy dx minus 32x squared y squared dy dx. I have 3 terms containing dy dx, and when I'm solving an equation that has my unknown in more than one term, I need to combine all of those terms on one side of the equation and everything else on the other. So I'm going to move these over by adding them. And then everything else is on the other side, so these terms stay on the other side. and I'm going to move this term over by subtracting it from both sides. Now that I have all of my terms containing dy dx on one side, I factor out the dy dx. I can divide both sides by this factor to isolate dy dx. Now I do notice that I have a common factor of 2 in the numerator and the denominator, so I could factor out that 2. And then when I cancel that factor out, I'm going to have my simplified answer. So we've now finished up with our inverse trig functions. We've previously done all the trig functions, found all the derivative formulas, and before I go on to other transcendental functions like log functions and exponential functions, I want to look at using these derivative formulas in some of the applications. So we looked at different applications before when we were working with algebraic functions and finding their derivatives, and those applications including finding the equation of a tangent line, using Newton's method to solve an equation, doing related rates questions, doing optimization questions, curve sketching. And I just want to do a few of those examples in the next video using our inverse trig and our trig functions, just so you can see how they work in those applications. So practice all of these trig and inverse trig formula questions, and when you're ready, I'll see you on the next video. Take care.